In this lecture, we will continue our discussion on homogeneous solutions. Suppose that some of the roots of the characteristic equation are multiple roots. Okay, for example, let's suppose alpha square minus 2 alpha plus 1 is equal to 0. It is a characteristic equation. Then we have alpha minus 1 square is equal to 0. Okay, which implies alpha is equal to 1 comma 1. Okay, so here the characteristic equation have multiple roots. Okay, not distinct roots but the multiple roots. So let alpha 1 be a root of multiplicity m. Like here alpha is the root of multiplicity 2. So let's suppose alpha 1 be a root of multiplicity m. Then the homogeneous solution of the recurrence relation is ARH is equal to A1 into R to the power m minus 1 alpha 1 to the power r plus and so on up to am into alpha 1 to the power r. So see here there are m terms are there because alpha 1 be a root of multiplicity m. In each term we have alpha 1 to the power r. Okay, so in each term the alpha 1 to the power r can be taken as common and can be written as a1 r to the power m minus 1 plus a2 r to the power m minus 2 up to am. In the bracket we have alpha 1 to the power r. Okay, so alpha 1 to the power r is taken as common from all the terms. Okay, we know that am alpha 1 to the power r is a homogeneous solution of the difference equation. In the previous lecture we know that for the difference equation, this is the difference equation. For this difference equation the homogeneous solution is, in the previous lecture we studied about am alpha 1 to the power r. This is the homogeneous solution for this difference equation where we set right hand side equal to 0. Okay, so instead of a we can write another constant, that is am. Okay, so since a is a constant we can write any constant, so we have taken here am. Okay, substituting am alpha to the power r for ar in the difference equation with the right hand side of the equation set to 0 we obtain. So in place of ar we will substitute am alpha to the power r. In place of ar minus 1 we will substitute am alpha to the power r minus 1 and so on, and with the right hand side of the equation is set to 0. So it can be written as c0. In place of ar we can write am alpha to the power r plus c1. In place of ar minus 1 we can write am into alpha to the power r minus 1. Similarly ck into, in place of ar minus k we can write am into alpha to the power r minus k is equal to 0. Okay, so here in this equation can be divided by this constant. Okay, so we can have am and we get this particular equation. So the whole equation is divided by am and we got c0 alpha to the power r plus c1 alpha to the r minus 1 and so on up to ck into alpha to the power r minus k is equal to 0. Okay, so we know that alpha 1 not only is a root of the equation 2 but also is a root of the derivative equation of 2. Okay, so alpha 1 is, we know that alpha 1 is the root of this characteristic equation 2, but also it is the root of the derivative equation of this equation number 2. So we will find the derivative of this equation with respect to alpha. So d by d alpha is equal to this equation c0 alpha to the power r plus and so on up to ck alpha to the power r minus k is equal to 0. So this derivative can be written as, so derivative of the first term is c0 r into alpha to the power r minus 1 plus derivative of second term is c1 r minus 1 into alpha to the power r minus 2 plus c2 r minus 2 into alpha to the power r minus 3 plus up to ck r minus k into alpha to the power r minus k minus 1 is equal to 0. Okay, so here we use the derivative formula d by dx of x to the power n is equal to n into x to the power n minus 1. Okay, so here we find it out, d by d alpha of alpha to the power r is nothing but r into alpha to the power r minus 1. That is this formula we have used in this particular equation. So let write it down this equation as 3. Okay, because alpha 1 is a multiple root of equation number 2, multiply equation number 3 by am minus 1 into alpha, and replacing alpha by alpha 1 we obtain. So here we'll multiply this particular equation number 3. Okay, we'll multiply this equation 3 by this am minus 1 alpha and replacing alpha by alpha 1. So we get, so here we can write it down like c0 am minus 1 r alpha to the power alpha 1 to the power r plus c1 am minus 1 r minus 1 alpha 1 to the power r minus 1 plus c2 am minus 1 r minus 2 alpha 1 to the power r minus 2 and up to ck am minus 1 r minus k alpha 1 to the power r minus k is equal to 0. Okay, so this is we got. We just multiply this equation by am minus 1 alpha and replacing alpha by alpha 1, we got this equation c0 am minus 1 r into alpha 1 to the power r and so on up to ck am minus 1 r minus k alpha 1 to the power r minus k is equal to 0. Okay, so which shows that am minus 1 r alpha 1 to the power r is a homogeneous solution. Okay, so here it shows that this particular am minus 1 r alpha 1 to the power r is a homogeneous solution. So how it is a homogeneous solution? So we know that the kth order difference equation is, the kth order difference equation is c0 ar plus c1 a r minus 1 plus c2 a r minus 2 plus up to ck a r minus k is equal to 0. You have to set the right hand side as 0 because you are solving the homogeneous solution. So this is the kth order difference equation with right hand side equal to 0 because we are solving the homogeneous solution. So see here, in place of ar we have am minus 1 r into alpha 1 to the power r. In place of ar minus 1 we have am minus 1, this is the constant that is the same, we have r minus 1 alpha 1 to the power r minus 1. In place of ar minus 2 we have am minus 1 r minus 2 alpha 1 to the power r minus 2. In place of ar minus k we have am minus 1 r minus k into alpha 1 to the power r minus k. Okay, so this particular am minus 1 r alpha 1 to the power r, okay, so this is a homogeneous solution. Okay, the fact that alpha 1 satisfy the second, third, m minus 1 first derivative equation of 2. So alpha 1 satisfy the first, as we saw in the last slide, alpha 1 satisfy the first order derivative of this equation 2. Okay, this is equation 2. This is the first order derivative, and alpha 1 satisfies this particular equation, but also alpha 1 satisfies the second, third, up to m minus 1 first derivative equation of 2, which enables us to prove that am minus 2 r square alpha 1 to the power r comma am minus 3 r cube alpha 1 to the power r up to a1 r to the power m minus 1 alpha 1 to the power r are also homogeneous solution in similar manner. Okay, so when we find out this second order derivative of equation 2, then this will be the solution. When you find out the third order derivative equation of 2, then this will be the solution, and so on. And when you find out the m minus 1 first derivative equation of 2, then this will be the solution. Okay, so we got that this is the solution, this and up to a1 r to the power m minus 1 alpha 1 to the power r. Okay, so these are the solution. So the homogeneous solution can be written as sum of those solutions. Okay, so in these terms alpha 1 to the power r is taken as common. Okay, and so here we have from here we can write it down. The first solution was am, so the first solution was am alpha 1 to the power r. That's the first solution we got, and the second solution we got here am minus 1 r. So this one is second solution, am minus 1 r alpha 1 to the power r, and the second solution, this is the second solution, and the third solution is am minus 2 r square alpha 1 to the power r. Okay, and so on. So when we find out the sum of this, then the sum of all the solution is also the solution of the recurrence relation. So this is so the homogeneous solution is ARH is equal to, this is the sum of all the solutions. So a1 r to the power m minus 1, so this is this term, it is written in the reverse order. So this is written here am, and alpha 1 to the power r is taken as common, because alpha 1 to the power r is common in all the terms. So this one is this. Okay, am minus 1 r, and alpha 1 to the power r is this. Okay, then am minus 2 r square, this, up to we have a1 r m minus 1, so this one, and alpha 1 to the power r is common here.